mute y'all if there's feedback. So here we come again to this half-life problem, and maybe you remember how to do this, but notice that there's two units here. We got this isotope, which is mixed with a cold bromine solution, and that's to keep it stable. Okay, when you have nuclear reactors, the rods that go down, they go down into a solution that inhibits the chain reaction. And soon, right, so that's why they're placed in this cold bromide solution. It's really toxic stuff. So the 200 gallons here is volume. So the weight of the isotope that we put in the cold bromide solution is 20 pounds. And that's going to decay over time. And so after 30 days, you have half of these 20 pounds left. So we're basing this on the weight, not the volume. Because we don't even know, well, we do know that this 20 pounds would not take up a total 200 gallons, right? Because we're soaking the isotope in the bromide solution. So there's more than just the isotope in this 20 gallons. Okay, so just to make sure we're clear, we're doing this based on weight, which is related to density, right? And the density is how much per volume. So you could do that, but we're not. We're just going to use 20. Okay, let me invite Sam in, and we'll get started. So we're getting to my favorite part of these type of problems. I'm kind of really excited about showing y'all some stuff from the data. That's probably going to happen on Monday next week. So just so you're aware the next 2 weeks, right? Today we're going to look at logarithmic equations. Thursday we're going to look at more advanced exponential equations. We've already been kind of dealing with these equations by just reversing to the exponential or reversing to the logarithmic equation. But the more advanced ones we haven't really looked at. So on Thursday, we'll continue to exponential, and then Monday, we'll do some modeling with exponential, and I'll show y'all some things that are based on exponential Euler's growth factor. Okay, and then we'll have our last assessment next week. Now, seniors, you don't have to worry about the last assessment, all right? Okay, so basically we want to find the half-life. And so we want to first figure out what the rate is going to have to be to model this isotope that decays by 50% in 30 days. So we're going to have half as much as we originally did in 30 days. So you could think of it like that, or you could think of it like, well, we started with 20, and then we had 10, and we know that took 30 days. So however you get there, notice that you're going to get the Euler equal to 1/2. So we solved this problem. All right, so we can solve that. We can now, if you want to just log both sides, you can start doing that. Or if you want to reverse it to the logarithmic equation. So our exponent's going to be 30r. Our value is going to be 1/2. Or if you want to just log both sides, you can get there too. Now, if you just switch it to the to the logarithmic, you can skip this step, which is why I showed you how to do that. Right. So now notice we got the exponent as part of the value. So the 30r multiplies to this, and I'm just going to make this 0.5 now. Oh wait, yeah, let me write that a lot better. All right, well, this right here is 1. Right, because if we're trying to represent e with base e, we need an exponent of 1. That equals 1. So now our problem is this. And then you divide by 30. Now there's a shortcut of half-life problems. Okay, so now we divide by 30. Okay, so the rate is going to equal the ln of 0.5 divided by 30. And so notice the shortcut. You want to find the half-life? When does this equal 1/2? That's the ln of 0.5 divided by the time it took to equal 1/2. So all of this that we just did, once you know that, you can just go right here. And then, of course, that's what people do. So then this is going to become a negative because we're decreasing. That's what a 50% decrease is. And this is what you would basically have depending on how far out you want to go. Now, what I did is I kept that number in my calculator. Right, so I didn't estimate it. But anyway, that's what that would be. All right, so how long is it going to take for us to have 1/100th left? So in other words, when does this, sorry. Sorry, that's a t variable. I don't know if that's, yeah. Okay, so, and if you want to think of it, why is that 1/100? Well, if we started with 100, we're going to have 1% when we have 1 left. So you could think of it like that. And so then you would divide by 100. And I'm just putting ... because it's the same as that. So if you're not quite sure why we have this equation, that's why. If we started with 100, we'd have 1 left. That would be 1%, which means we're solving this problem. And just to repeat myself, that ... is just what is written there. Okay, so then you can do the same thing we did here, ln of both sides. And notice it's going to become the ln of 0.01 divided by that negative 0.023. So this is what we're going to get when we finish that. But I need to go a little slow. All right, and then this multiplies to the log, because again, the exponent's part of the value. And then we get the ln of e, just like we got here. Okay, and then you divide. And you should get 199.135 days. Now, some of these substances are so toxic that we really wanted to get less than a micron, which would be 10 to the -6 power. Right? Your hair follicle is 50 microns. The coronavirus is 0.1 micron. Okay. But imagine if this was 30 years. This would be how long we'd have to wait just to have half left. I mean, sorry, just to have 1% left. So again, you know, the issues with radioactive waste it's just inescapable. You don't know what to do with it. Okay, everybody all right with that? All right, y'all. So I guess we can look at the homework now. So I guess I got to share a screen, remind myself what buttons I have to push. And this might be something that y'all are familiar with. But anyway, just as before, doing this homework solutions for everybody. You only had the odds. All right, is there any particular homework problem you want me to go over here? There's a couple that I definitely want to go over, but I want to make sure. So 21. Oh, yep, definitely was going to go over 21.
11 too.
Was one of the hard ones. Come on, Tiger. There you go. Okay, well, for a little while, not too bad. It's just basic straight application. Notice the exponent is part of the same base, so 71. Okay, and then now look, the number 11, we're applying to base 2 a logarithmic that uses base 2. So the log base 2 of 7 is the exponent you apply to 2 that equals 7. That's why that equals 7. So 2 to this exponent would give you 7. The log base 2 of 7 will give you the exponent. So you apply that exponent to 2, you get 7. So I'm trying to say that in other ways, but is that all right, Pat? You asked about that? So basically, if the base and the log base, if those are the same numbers, it equals the value. They don't really cancel each other out. It's not really what's going on. You're applying the exponent to the base that will get the value is really what you're doing. All right, and again, notice that if the value and the base are the same, you equal 1, just like the ln of e was 1. Right? And then this one, you had to use the change in base property, which enabled you to divide off the log 6s. And then here, it'd be a good idea to convert 4 to 2 squared. That way you have the 2's. And then once you get to this point, now you can reverse the change in base property. And so now the logarithm is based on the 2. So 2 squared means the exponent's 2. There's a whole lot of 2's, so that might be a little troubling. And then here, with 19, the exponents are from logs that use the base 3. And so since we're subtracting, that means it originally was the 5 divided by 4 as a value. Okay, and now since we're applying the log to a base 3, when we are using a base 3, this should equal 5/4. Because again, this is the exponent to 3 that you would use to get 5/4. So if you put that exponent to 3, you get 5/4. As long as these two numbers are the same, then the value is the answer. Now 21 is a little more involved because unlike 11 and unlike what 19 eventually became, you're applying an exponent to a base e, but the log is based on e squared. So this can't equal 16. E and e squared are not the same. All right, so what you want to do here is you can switch it to the logarithmic equation, or if you want to ln both sides, you'll still wind up to this location. So notice the values what the e to the exponent equals. The exponent is that log. And since the base is e, we use ln. So the ln gives us this exponent. All right, so now we can use the change in base property for this stuff on the right. So this is how we get. Now I wrote this as log base e just to be a little more obvious. Okay, and so now we can go ahead, since we have the log e squared on the bottom, now we can use the property of logarithms. The exponent is part of the value, so the 2 multiplies to the log of e. And now we can reverse the change in base property. So now we can change this to log 16 base e. We still have the 1/2 multiplied in front. And now we can do the property of logarithms. We got a 1/2 multiplied to a log, so that originally must have been the exponent of the value, 16. Square root of that is 4. Okay, so now that these two are equal and they're using the same base, the value's got to be the same, so 4. And you could think, well, if we're squaring the base here, then you don't need a full 16. You can get by with a 4, which would be the square root of 16. So you kind of reverse the squaring by square rooting. A little awkward, I guess, to think about that. But anyway, this is how you can do all that. Is that okay, y'all? I mean, I think I kind of provided a sufficient amount of steps, but I know this is new to y'all. All right, so this first step is the key. And then using the change in base property, that enables you to get the 2 off of the e, right? And so now you can reverse it back, and now you have the logs both based on e. That's essentially what you're doing. Okay, cool. Thanks for the confirmation. All right, and here you're just changing what they give you to be using 2's and 3's, right? And then you can represent it with the letters A and B. This, by the way, is a favored question on the SATs. They like to do this kind of stuff. Okay, so same thing here. So you want to now rearrange it. Yeah. Okay, so here it's just a matter of expanding. Right. right? So with 39, first you got to do the multiplication. So you can't do the powers first, because the first thing is u squared times v cubed. So that's why this is plus, right? Okay, now you can do the powers, and then now you get down to the end 39. Okay, and then same thing here, 41. You got to do the multiplication first. So the x squared, and then this is the square root of 1 minus x. I just wrote the 1/2 power here. And now you can do the exponents. Okay, and then you can see down here, starting with 43. Now they went ahead and defined the domain for you. So we could do that, right? So again, you can't have negatives here. So x can't be 0. And it's got to be where x minus 3 is greater than 0. So that's why it is. And again, that's true for all of them. And just be careful. Remember, you might have to do a numerator equals 0, denominator equals 0, test points in the number line. And so this was the only one that would have worked. But anyway, you didn't have to worry about that. They did it for you. All right, so notice here with 49, first you want to do the division. So that's why the minus. And then you want to break apart the multiplication that occurred here on the left. So I'm talking about 49. Okay, so when I went ahead, and since 5 times x is 5x, that's why I did ln 5 plus ln x. And then here, the next part was the 1 plus 3x, and I went ahead and put the 1/2 in front. So I did kind of 2 or 3 steps at once here. Okay, and then the tricky one may be on the bottom. So here's what you wanted to contract. In other words, shrink down into a single logarithm. Right, so first one thing you want to do is you want to take the 8 and put that as an exponent to the value, but since that's a 1/2, that's going to become 8 times 1/2, and so that's why there's a 4 here. And then since you're minusing, that means numerator over denominator. And I went ahead and I wrote 8 over x as 8 times x to the negative 1. That's why that's there. So we get here. Right, and then it's just a matter of simplifying in here a little bit. So if it's 8x negative 1 on the bottom, that means x on top. And if you got an 8 on bottom and a 2 squared on top, that means 2 on bottom. And so that's how that happened. I kind of tried to squeeze that in the lower right corner. Okay, everybody good? All right, we're going to look at one thing today, and then we'll do the rest of it on Thursday. So we're going to look at logarithmic equations. Okay, and so that would be when you have two things. Now, I also provided this, but we're not going to get to this stuff on the bottom till Thursday. So we're either going to have a log equal a number, or we're going to have a log equal a log. And so these are the two types of log equations. All right. So we'll look at probably 4 examples. I think that'll probably be okay. We could probably get by with 3 if time was an issue, but we'll see. I don't think time's going to be an issue. Okay, now when you have log equal to a number, then you can just reverse it to the exponential. But if you have log equal log, then you reverse logs, and then you'll get the two values equal to each other. So that's the difference. One, you got to reverse to the exponential, the left, log equal number. The other, you don't have to reverse to the exponential, because you can just reverse logging both sides. Okay? All righty then. So let's say we had log x plus 4 equals 2. Okay, so now we want to rearrange this. So we got our exponent, which is 2. The value is x plus 2, and then the understood base here is 10. All right, so 10 squared equals x plus 4. And then you just solve it after that, which I know you can do, 100 minus 4. So this is a log equal numbers equation. All right, now let's look at a log equals log equation. I'll take a sip of water. All right, so let's say we had 2 log base 5 of x equals 3 log base 5 of 4. Now, since these two bases are the same, then we just got to get the logs equal to each other. If these two bases were not the same, then we still got to get the logs equal to each other, but then we'll have to do the change in base property, which just basically converts to log base 10 when you use the change in base property. Okay, so we got this 2 and this 3. Those originally were exponents to the two values. The first thing we want to do is reverse that logarithmic property. So the 2 is now the exponent of x, and the 3 is now going to become the exponent of the 4. All right, so now you have the same function, log function based on 5. And so the two values have to be the same, so you can reverse logging both sides. Right, and so then I think 4 cubed is 64? Yeah. And so so 8. Okay, well, let's look at 2 more. All right, so let's say we had log base 2 of x plus 1 plus log base 2 of x plus 7 equals 2. So this is going to wind up being a log equals number equation. And so what we have to do is contract the left side to get a single log. They're both based on 2. So we can immediately apply the property. So if we're adding logs, that means originally the values had to be multiplied. Okay, now we got a log, and this is the value, equals to 2, so the exponent's 2. The base is also 2, and this is the value. Okay, so 2 squared equals, and then you just solve that, which I know you guys can do, right? You're going to wind up with the quadratic equation, subtract 4. You might be able to get a zero product property, or if worst comes to worst, you can do the quadratic formula. Okay, any questions on that? Again, I'm just assuming you guys are able to solve that, which I think is a good assumption. Okay, one more. Now, we haven't used ln yet. And so let's say we had ln, and this time we'll subtract instead of add. Now, a lot of times people won't write parentheses here. They won't usually do that. I'm doing it, but sometimes people don't do that. All right, so now again, just as before, we're going to have a log equal number. So we're going to have to contract the left side. Since that's minus, that means the left value is the numerator and the right value was the denominator. Okay, now here's where it gets fun. We need to rearrange this, but we're going to have to use Euler's number, which is not intuitive. And we know the exponent is 2. And this is the value. Now, I'm not going to simplify that just yet. All right, so then e squared equals that. Now, how do you handle that? Well, you could put a 1 here and cross multiply. Yeah, that'd probably work. That'd be okay. But instead, since the denominator is just a single value, I'm thinking, let's go ahead and simplify this first. All right. So e squared. So if we divide, this is going to become 1 plus 1 over x. Okay, now what we got to do is subtract 1, and then we can just do the reciprocal. All right, so and now we can just reciprocal both sides. Okay, so that's the answer. Okay? All right, well, this is basically the homework. And again, you only have the odds to do. And we'll worry about the more advanced exponential equations on Thursday. All right, well, almost there, y'all. Okay, so seniors, hang in there. Are there any seniors here today? Yeah, there is. Hi, Tori. Hi, Sam.
Hi.
Did I miss anybody? I don't think I did.
Mr. Napoli?
All right, y'all, we're good. Y'all need anything? Anybody need me to address something? Anything you're not sure about? Okay, y'all. I'll see y'all later. Y'all take it easy.